Hi, this is Mrs. Kidman, and in this video, we are going to be discussing what happens when we graph f of x, but not just f of x, but what happens when there's an a in front of that x squared. So before we do that, let's take a look at a reminder of what our function x squared looks like, or our quadratic function. So here's our parent function, and again, we can write it in function notation, so f of x equals x squared. Now, I just want to take a look at what does this graph look like. So how we do that is we're going to substitute these values in for x, and then whatever their output value is, that's what we're going to graph on our y-axis. All right, so if I put 1 in, 1 squared is 1, 2 squared is 4, 3 squared is 9, 0 squared is 0, 1 squared is 1, negative 2 squared is 4, and negative 3 squared is 9. Notice this pattern here, that they kind of circulate around that 0. So we start here at 0, 0, and we talked about this in the previous video discussing those characteristics of these quadratic functions, that they're actually going to be symmetric about that vertex point. And so our vertex here is going to be at 0, 0, and we're going to be symmetric. So as I go over 1, up 1, and that's going to happen in both directions, over 2, up 4, in the positive, over 2 up 4 in the negative, over 3 up 9, over 3 up 9. And we can see that it makes this beautiful parabolic shape. Now, as we graph this, this is just our x squared. And what you're going to notice is whenever we have functions that look kind of like this, we actually talked about when we looked at those absolute value functions, how a affects it. And with those absolute value functions, our a affected it like our slope. It switched it from being open up to being open down. It made it have a vertical stretch or vertical shrink. And we're going to see that this a here does the exact same thing. So when we're looking at this function, f of x equals a times x squared, what happens is we have two conditions. When a is bigger than 0, and then we also have when a is less than 0. And they have two different characteristics there. So when a is greater than 0, two different things are going to happen. If that number is between 0 and 1, so 1/2, 2/5, 3/4, anything like that, if it's between 0 and 1, so we see a fraction there, what's going to happen is we're going to have a vertical shrink. So remember our rubber band example. If I have a rubber band and I take the top and I'm holding it between two fingers and I take the top of it and I shrink it down towards my two fingers, notice how the function gets wider. That's what you can see happens here with this red function. Our blue one is our parent function. So this blue one is our f of x equals x squared. Now that red function is what happens when it's a fraction for a. It's going to get wider. We have that vertical shrink happening. And what that vertical shrink means is instead of right here being 1, instead of going up 1 over 1 like we do on our parent function, what's going to happen now is we go over 1 and then we go up less than 1. It doesn't go as high. We're shrinking the height that it climbs when we go over 1. On the contrary, our green graph up here is what happens when a is greater than 1. Oh, and when a is greater than 1, what's going to happen is we call it a vertical stretch, and that's coming back to that rubber band. When I stretch out a rubber band, what happens to it? It gets thinner, and that same thing happens with my function. So as I have a vertical stretch, what that means is as I go over 1, what happens is I'm stretching how far up I go. In this graph, instead of going over 1, up 1, I'm going over 1, and notice how high up I end up going. Okay, I stretch how far it goes when I go over just one step. Now, on the contrary, when a is less than 0, notice what happens here. When it's greater than 0, it opens, it's going to open up, right? And I like to think of that as a is positive, because that's greater than 0. If a is positive, it looks like a smiley face, right? Opens up. If a is negative, the biggest thing that we notice is that it's going to open down. Or if it's negative, it looks like a frowny face. It opens down. So you can draw these cute little eyes. It opens down. So as we are looking at this function and we see when a is negative, the very first thing is it opens down. That's what happens. And then we look at the two conditions. So just like before, if a is a negative fraction, so a negative 1/2, a negative 3/4, a negative 1/16, we are still going to have that vertical shrink occurring for us, right? The distance we have to go when we go over 1 is going to be less than it would be if we were looking at our parent function there. Similarly, if a is, we say less than -1, so really -2, -5, -10, if it's more negative than -1, then what happens is we have that vertical stretch that occurs. And so as we're at this 1, instead of going over 1, up, down 1, we're going to go over 1, and we're going to end up going down further than 1. We're going to stretch how far it goes. And so just like with those absolute value functions, this a will affect whether it has a vertical shrink and it gets wider, or vertical stretch and it gets thinner. So I want to take a look at a couple of examples here of what happens when we have this ax squared. So this first one here, I want to compare this g of x equals 2x squared to the graph of f of x equals x squared. And to do that, I want to just start by graphing it. So here's my g of x equals 2x, my x squared. Let's draw a quick little axis here for us. So I've got my axis grid here. And what I'm going to do is I'm just going to create a table. So here's my f of x table. What happens when I have x values and y values? Now I'm just going to graph from -3 up to 3. So I'm going to graph these 7 points here. And I'm going to do it on both my f of x graph, and I'm also going to do that on my g of x graph. So here's my x values, here's my y values, and let's graph them. -3, -2, -1, 0, 1, 2, 3. Okay, let's see what happens here. So as I substitute my values in, I know for my x squared, -3x squared is 9, -2x squared is, -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 2, or 2 squared is 4, and 3 squared is 9. Now let's look at it over here. I'm going to plug these values in just like I did before. -3 squared is 9. 9 times 2 is 18. -2 squared is 4. 4 times 2 is 8. -1 squared is 1 times 2 is 2. 0 squared is 0. 0 times 2 is 0. 1 squared is 1 times 2 is 2. 2 squared is 4. 4 times 2 is 8. And 3 squared is 9. 9 times 2 is 18. So here we are. We're going to graph it. Now I'm going to graph my g of x with this blue line and my f of x with this green line. So I'm going to start with my f of x here. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We're going to kind of start there. I've got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now remember that our graphs don't have to look perfect. We're just trying to get an idea of what this is going to look like. So I'm going to start with my green graph here. So it has a vertex right here at 0, 0. And then as I go over 1, up 1, next one is 2, 4, and -2, 4, and then 3, 9, and -3, 9. So here is what that f of x graph looks like. Boom. There we go. Now let's compare it to our g of x. So as I graph this, this still has that same point, 0, 0. But as I go over 1, instead of going up to 2, or instead of going up to 1, it stretches all the way up to 2. And then when we go over to 2, we actually get all the way up to 8. So -2, 8. And then when we get to 3, we're actually going to be totally off our graph, like way up here. And so what this graph ends up looking like is it ends up looking like this. So you can see that what happened here, our pattern that we observe between our g of x and our f of x is they have the same vertex. But what happens is by multiplying by 2 here, it still opens up just like we saw before, but each of our values is multiplied by 2 in our original function to get us to our g of x y value. Right? And that is how we got our 18, our 8, our 2, our 0, and all of those because we had to multiply each piece by 2. So notice not by 18, by 2 gives us 18. So notice, whatever this number is here, whatever our a is, what's going to happen is we are going to take our parent function values and multiply them by that. So let's graph and compare. Notice they both still increase and decrease at the same place. They still have a vertex at 0, 0. The biggest thing that happened is when it was greater than 0, we had, and it was greater than 1, we ended up having a vertical stretch and our function got thinner. So let's take a look at this next one. We are going to kind of do this next example all together again. So just like we did before, we're going to multiply it. So now I have h of x, which is negative 1/3 times x squared, and our f of x squared. So I'm going to graph these. Here's my f of x, and we're going to do our x and y value table just like we did before, and our h of x, and we'll do that x and y value table just like we did before. And over here, we will have our graph. And I'm going to wait to draw those lines until I figure out what numbers I need. So -3, -2, -1. As a rule of thumb, just try to do those numbers surrounding 0, especially when we just have an a value. So I'm going to do from -3 all the way up to the number 3 here. And as I plug it in, remember our parent function is going to give us a 9, 4, 1, 0, 1, 4, 9, right? -3 squared is 9, -2 squared is 4, -1 squared is 1, etc., etc. We've done that a couple times already. Now let's do this again. Remember, our h of x is going to be whatever these values are times -1/3. So we're going to multiply each of these times -1/3. And that'll tell us what our function is going to look like here. So I'm going to look at what is each of these times -1/3, because that is what our equation tells us. So 9 times -1/3 gives me a -3. 4 times -1/3 gives me a -4/3. 1 times -1/3 gives me a -1/3. Anything times 0 is 0. -1/3, -4/3, and then we get a -3. So as I'm graphing this, I've still got my 1, 2, 3. I've got my -1, -2, -3. This middle is 0, and I only have to go down to 3. So I'm going to actually do this one in thirds. 1, 2, 3. This is -1, 1. This is -2. This is -3. And here's what our function looks like here. So I'm going to graph f of x in blue, h of x in green. So my f of x, I'm going to graph just like I normally do. 1, 2, 3, 1, 2, 3. Okay, we're going to graph this just like we usually do. So I go to my 1, I'm going to come up 1. My vertex is still at 0. 2, I'm going to come up to 4. 3 is going to be like way off my graph over here. So I'm just going to stick with these first 2 that I have. And this is what that graph looks like. Okay, so there's our parent function. There's that f of x. Now let's graph our h of x. So we start here at our vertex at 0, 0. At 1, we go down -1/3. At 2, we go down -4/3, or 1 1/3. And at 3, I go down to -3. And then similarly, -1, -1/3, -2, -4/3, -3. Okay, and here is what my function ends up looking like. Notice what happened here. 2 things happened. We are now open down as opposed to the blue one, which opens, as opposed to our blue one here, which opens up. The other thing is that this function is a lot wider. It had a vertical shrink. The distance that we went at 1, instead of being 1 here, is now 1/3. So we went a third of the distance. So we had a vertical shrink there. And that's kind of what happens with these graphs. So on these next few examples, what I want you to do is I'm going to take a second, work out the solution. I want you to pause the video, try to work out the solution on your own. After you finish working out the solution, unpause the video, wait a couple of seconds, see the solution pop up, and I will walk you through what happens. And I want you to compare it. So we can we're going to graph the function first and then compare it. Use that XY table. I'm going to draw an approximate look of what it looks like based on what we have, but draw that XY table so that you know exactly what our function is going to look like. Okay, hopefully you had a second to graph this and compare what these graphs look like. So as we're comparing these graphs, here's what my graph looks like. Notice how this 5x squared had a vertical stretch, and that vertical stretch was by a factor of 5, right? It got 5 times thinner than that original function. So I want you to go through these next two, graph them, see what happens, and then unpause the video and we will double check them together. Okay, hopefully you've had a chance to look over these. Here, as we evaluate these, notice that this one, with our h of x, we ended up with a vertical shrink on this one. And then our function here got wider, right? We had this shrink where the distance that it went when it went over 1 decreased to 1/3 instead of going over 1. This next one is a little bit tricky because a lot of us see this 3/2 and we think it's going to shrink. But what actually happens when you plug those into a table is 3/2 is actually bigger than 1. And when we go back to this, if a is bigger than 1, which it is in this case, we are going to end up having a vertical stretch here. So we did end up stretching in this case. Now, as you look at these other examples, it's going to be the same thing, but just remember that these negative signs tell us that our function opens down. So if you want to work through these problems, feel free to work through all 3 of these on your own. When you finish, unpause the video and I will have the solutions worked out for you. Okay, hopefully you had a chance to work through these as you wanted to. Remember that as we look at these 3 functions here, these new functions, notice how when we have that negative sign, it opens down every time. If the number after the negative sign is bigger than 1, so a -3, a -7, we are going to have that vertical stretch and it's going to get thinner. If we have a number that is less than 1, so a -0.1, a -1/4, whatever it is, it's going to stretch out compared to our other function. And that's what happens with our a here. So as we multiply some number times our x squared, depending on what that number is, if it's positive, it'll open up. If it's negative, it opens down. If it's a fraction between 0 and 1, so 1/2, 1/3, it has a vertical stretch by that factor. So it's going to be that number times our x squared. If it's bigger than that, it's going to have a vertical shrink and a vertical stretch and it's going to get thinner. And that's what happens when we have to graph with an a in front of our x squared function.